might recall that a covalent bond forms when two atoms share their electrons. All right, that seems simple enough. However, the problem is that that's not the most accurate representation of what's happening in reality. In reality, recall that hydrogens, they have orbitals, right? Regions where electrons are most likely to be found, right? So the fact that, saying two atoms, they share their electrons isn't kind of the most accurate way to represent things. And valence bond theory kind of says that, well, covalent bonds form when the orbitals of different atoms, they overlap with each other. And that's what creates a covalent bond. So sort of an accurate representation of what's happening is, recall that hydrogen only has one electron, right? So that means that the electron configuration for hydrogen is 1s1, right? It has one electron in the 1s orbital. And same goes for the other hydrogen. Now, what happens is that this 1s orbital it's going to get closer, right? These atoms are going to move towards each other. So these 1s orbitals are eventually going to get closer and closer to each other, and then they're going to overlap. And basically, this overlapped region is a space where the electron density between the two nuclei of the atom, the electron density is going to increase in this overlapped area. And this basically creates like a shared region of space, and that's basically covalent bonding in terms of the valence bond theory. All right, it's this overlapped area between the two orbitals where the covalent bond sort of happens. Now, when we draw out H2, right, like this, notice how there's only a single bond, right? H2 has a single bond. And it turns out that all single bonds are something known as sigma bonds, right? All single bonds are sigma bonds. And essentially what a sigma bond is it's basically when you have these two orbitals and they overlap head to head. So notice how, right, you have these two atoms, they're moving towards each other, and the two orbitals overlap head to head, right? And it turns out that all single bonds have this head to head overlapping. And that's something known as a sigma bond. Right? Sigma bonds occur when there's head to head overlapping. And that's something known as hybridization. Okay? Let's take a look at CH4, methane. CH4 looks something like this if you draw it out normally. So if you draw it out normally, looks something like this. Okay. But wait, remember that this isn't actually the most accurate way to draw out CH4. Recall that we have something known as VSEPR, VSEPR theory, right? And this basically states that essentially, right, the molecules are in 3 dimensions. So, I mean, in reality, we're representing CH4 in 2 dimensions, but in 3 dimensions, right, this is what CH4 would look like. So this is how CH4 would look in reality, okay? So yeah, you have the carbon in the middle, right? And then you have this hydrogen going upwards. Then you have this hydrogen going down to the side, right? So down to the side here. Then you have this hydrogen right over here going into the screen, right? You see how it's sort of going into the screen. So that's why I drew this little triangle thing here to indicate that it's pointing towards you, right? It's literally pointing towards you. And then this dotted triangle basically represents that it's pointing sort of away from the screen. So it's pointing away, behind, right? It's pointing behind from this screen. And it turns out that the angle that it creates, right? So the angle between this hydrogen and this hydrogen right over here, it's a 109.5 degree angle. And that's true for every one of these hydrogens. Because valence bond theory focuses on orbitals, I've written out the electron configuration for carbon. Carbon has 6 electrons, so the electron configuration is 1s2, 2s2, and 2p2. If I were to write this on an orbital diagram, right, you have your 1s orbital at the bottom, you have your 2s orbital that's a little bit higher in energy, and then after that, you're going to have 3 2p orbitals, right? Now, the thing is that, right, the first orbital is going to be completely filled with 2 electrons, and so is the 2s orbital. And then for 2p2 orbital, well, there's only 2 electrons reserved for that, right? So there's going to be 1 electron in one of the orbitals, another electron in another orbital, and then this last orbital gets no electrons because you used up all 6 of your electrons. Now, yeah, there's 3 2p orbitals in case y'all were wondering, right? That's why when you're writing out the electron configuration, right, it's 1s2, 2s2, and then 2p6. Or the reason why it's 2p6 is because you have 3p orbitals, right? Each orbital can hold 2 electrons. So 2 electrons multiplied by 3 orbitals, 2 times 3 gives you 6. So in total, all these 2p orbitals can hold 6 electrons. Now, the problem with this right over here is, all right, we're not really going to be focusing on the 1s orbital because that's the lowest energy level, right? It's sort of like when you're focusing on bonding, right? Covalent bonds, you're only focusing on the valence electrons. So in this case, I'm only going to focus on the I'm only going to focus on these orbitals because these are the higher energy orbitals, right? So I'm not going to focus on the 1s orbital. Problem with carbon has, imagine if I have carbon right over here. It has 4 valence electrons, right? It has 1 electron here, it has 1 electron here, and it has 1 electron here, and 1 electron here. So it's able to share these electrons and form 4 bonds. But the problem is that I have these 4 orbitals right over here, right? But the problem is that you have 1 orbital that has 2 electrons. So that's kind of like the equivalent of saying if I have carbon right over here, and let's just say I have all these hydrogens, just to simplify things. This right over here is the equivalent of, let's just say, one side having 1 electron, the other side having 1 electron, this side having no electrons at all, and then the last side having 2 electrons. You kind of see what where I'm getting at, right? This right over here is sort of like the equivalent of this, right? One side has 2 electrons, and then you have 2 sides with 1 electron, and then one side just has no electron at all. So how is this supposed to work, right? So what sort of happens is that the 2s orbital is going to give one of its electrons to the 2p orbital. So it's going to give one of its electrons to this 2p orbital without an electron. So now everybody has an electron, right? Everybody has an electron. There's still a problem with this, all right? And the problem is that these orbitals are not the same, right? When we're talking about the VSEPR theory, right? Notice how all these bond angles are the same. However, in this case, notice how all of my orbitals are not the same, right? I have this 2s orbital, and that's different from the 2p orbitals. So therefore, the shape of my CH4 molecule, if I were to actually draw this, would be different from what the VSEPR theories. So that you can imagine, this is the carbon atom right over here in the center. And recall that there's 3p orbitals, right? So there's going to be 1 p orbital here as shown in the white. There's going to be another p orbital here shown in the yellow. And then there's going to be 1 p orbital here shown in the green, right? Imagine if we were to draw like an axis, right? A 3-dimensional axis, right? In like graphing, right? Graphing linear equations, right? For example, you have an x and you have a y-axis. 1 p orbital is going to be along the x-axis. The other is going to be along the y-axis. And in the final orbital, the third 2p orbital is going to be along the z-axis, right? It's going to be 3-dimensional, right? And then don't forget that we also have the 2s orbital. What the hell does a 2s orbital look like? Well, if you recall a 1s orbital, it's basically, it looks like a sphere. It's actually a little bit different. It's going to be a sort of bigger version of the 1s orbital, but there's going to be a slight change. But it's going to be like a bigger version of sort of like the 1s orbital. Then there's going to be like a node. A node is basically a region where electrons can't be found, right? The probability of finding an electron there is 0. And then after that, then it goes on. So it kind of resembles the planetary model, right? Where there's just empty space in the middle, right? So if I sort of incorporate that there, well, first of all, before I do that, remember that I'm drawing CH4. There's 4 hydrogens that I have, right? There's, let's say, 1 hydrogen here, 1 hydrogen here, and 1 hydrogen here. Let's see how this bonding will work. The hydrogen's 1s orbital will overlap with this p orbital. This hydrogen will overlap with this p orbital. This hydrogen will overlap with this p orbital. And then for the carbon, we still have remember, we still have a 2s orbital remaining, right? We still have this 2s orbital that I have not drawn yet. And the reason why I have not drawn that yet is because here's where, things have already kind of gone awry, but here's sort of where things get awry even more. So this hydrogen's orbital will overlap with the hydrogen's 1s orbital will overlap with the carbon's 2s orbital. But the problem is that there's not really a set angle. So look, the hydrogen and the carbon, their orbitals can overlap, right? Imagine if these two orbitals overlap. Okay, imagine if these orbitals overlap. Okay, that's cool. But the problem is that the overlapping doesn't have to just take place in this one area. So, right, this hydrogen, when it overlaps with this 2s orbital, notice how in diagram 1, it approaches it from this angle, right? But notice how in diagram 2, this hydrogen approaches the the carbon atom from this angle now. And notice how there's not really a defined sort of angle that, the CH4 molecule takes on, right? So this is the problem, all right? CH4 without hybridization, the s orbitals don't really have a set direction. The hydrogen would approach the other spherical 2s orbital, and they can overlap at any sort of direction. So there's not really a set sort of angle that's established between the s orbital and the 2s orbital, and that's going to lead to angles that are different than 109 degrees, 109.5 degrees, right? And in addition to that, another reason is because p orbitals, they are 90 degrees from each other, right? Remember how I talked about there's one p orbital on the x-axis, one p orbital on the y-axis, and then another p orbital on the z-axis. Well, all of these orbitals are 90 degrees from each other, and that is different from the 109.5 degrees that we have established. So what is going on? What's going to happen is that all of these orbitals are going to hybridize, or they're going to combine, right? They're going to create a new orbital, are going to combine. These three 2p orbitals and this one 2s orbital is going to combine to form 4 different orbitals, right? You put in 4 different orbitals, and you're going to get out 4 different orbitals, right? Put in 4, get out 4. Now, these orbitals are called sp3 hybridized. So all these orbitals are called sp3 hybridized. And you can guess why they're called that. You used 3 2p orbitals, you used 3 p orbitals, and 1 s orbital. So they're called sp3, right? They're going to be a little bit lower in energy than the p orbitals, but they're going to have more energy than the s orbitals, right? Because they have, the way you'd say this is they have 25% s character, 25% s character, and they have 75% p character, right? Because you have 4 orbitals. One of them is an s orbital, so that makes up 25% of it, right, of the character, and then the other 3 make up 75% of it, right? So it's going to have a little bit of s, a little bit of p stuff, and ultimately their energy level is going to be sort of in between these two things, right, these two energies, but it's going to be very close to the 2p energy because it has a lot of p character, so it's going to be very close to the energy of the 2p orbitals. And each of these orbitals is going to have 1 electron, like what happens here, right? Each of these orbitals are still going to have 1 electron so that they're able to share, right? Now we said how this hybridized orbital has characteristics of an s orbital and a p orbital. Recall that s orbitals, they are spherical in shape. P orbitals, they are dumbbell shape. So when you kind of hybridize them, you're actually going to get something a little weird. Imagine a p orbital, except one lobe is bigger than the other, is an sp, that's an sp3 hybridized orbital. That's actually how it looks like. And in fact, that's actually kind of how, if you put 1 s orbital and you put 2 p orbitals together, that also kind of looks like this. In fact, any sp sort of hybridization that occurs, it's going to look something like this, all right, where one lobe is bigger than the other, all right? So any sort of sp hybridization that goes on, we'll explain more about that later, the different sp sort of hybridization and the sp2 hybridization, but it's going to look something like this, okay? So we are going to have, right, 4 sp3 orbitals. So it's going to be, sp3 looks something like this, right? One lobe is bigger than the other. It turns out this big lobe is going to be pointing out. This is the part of the orbital that's going to be overlapping with the hydrogen, all right? The big part is always pointing outwards. Let's say you have one lobe pointing out towards there. Let's just say you have another lobe pointing out, and it's going to be pointing out towards this side. You're going to have one lobe pointing out towards this side, and another lobe pointing out towards this side, right? And then you're going to have the hydrogens going in, right? Because this is CH4, you have 4 hydrogens. They're all going to have their s orbitals. Everything overlaps, and then we're all good, all right? because all of these orbitals are the same, we're going to have the same bond angles. And therefore, this is what gives me the 109 degree and 109.5 degree bond angles. Okay. So essentially, with the valence bond theory, we solved the problem of one orbital having too many electrons, and we also solved the problem of uneven bond angles, right, due to hybridization. Hybridization has saved us from uneven bond angles, and now we have all of these orbitals right over here overlapping with the hydrogen's orbitals and creating the even bond angles. Also notice how all of these bond angles right over here, all of these sort of overlapping happens head to head, right? All of these overlappings are head to head, right? All of these overlappings are head to head. So there's one head to head overlapping here, 2, 3, and 4. Therefore, CH4 has 4 sigma bonds, aka 4 sigma bonds is also, it looks something like this. Sigma is this symbol, so 4 sigma bonds. And this makes sense because recall that CH4, the structure for this is something like this, where it has 4 single bonds. And remember that all single bonds are sigma bonds, right? Single bonds contain 1 sigma bond. So 4 single bonds, 4 sigma bonds, that matches up. And boom. In the last example, we saw that sp3 hybridization is used for tetrahedral structures, or 109.5 degree sort of angles, right? Bond angles. In this example, we are going to be taking a look at sp2 hybridization, and that's used for 120 degree bond angles. So trigonal planar, right? This is an example of trigonal planar. This molecule is ethene. It's trigonal planar. Okay. So we want to make sure that whenever we're doing our sort of orbital thingies, whatever, it's going to follow the VSEPR rules. Okay. It's going to line up with the angles that are associated with that. Once again, we're dealing with this carbon. Let's just say we're going to mainly be focusing on the carbons because those are the ones that are going to be hybridized. Hydrogen, it only has 1 electron. It can't hybridize. So if we're going to look at carbon, right? Once again, carbon is going to have the 1s orbital, 2s, and then 3p orbitals, 2p orbitals, right? And once again, what's going to happen is that carbon is going to promote one of its electrons to the third 2p orbital. Okay, that's the first step. This is just so that every orbital is allowed to bond, right? If the 2s orbital looked like this, right, this orbital would not really do anything. So yeah, once again, same step, carbon promotes one of its 2s electrons to the 2p orbital. Then, as you would expect, I said that this is going to be a sp2 hybridization. So 1 s orbital and 2 of the p orbitals are going to come together to form sp2, the sp2 orbital. So this is going to become, I'm going to ignore the 1s because I'm too lazy to draw it, but just know that the 1s orbital is still there, but it's not participating in any of the bonding because it's just so low in energy, right? We're only going to be focusing on the valence orbitals, right? The orbitals in the outermost shell, quote unquote. All right. So we're going to have 3 orbitals, right? Because this is sp2 hybridization, we use 3 orbitals, we get out 3 orbitals. So this is going to be sp2, right? Each of them are going to have 1 electron, right? Like before, and there's going to be 1 more 2p orbital, right? This is 1 2p orbital that is unhybridized. So there is going to be 1 2p orbital that is unhybridized and still has its 1 electron. And now look what happens, right? If each carbon, so this is the carbon sp2 hybridization, right? And if both carbons do these, well, this is how it's actually going to look like. And also, just a quick note, because this is sp2 hybridization, recall that any sort of sp2, sp3 hybridization, any of that, that's going to kind of look like this, all right? Each of the sp hybridization is going to look like this, where one lobe is bigger than the other. So the sp2 hybridization is sort of going to, I'm just going to model it as sort of the same shape as the sp3 hybridization. And in addition, we have 1 s orbital and 2 p orbitals. So this is going to be 33% s character and 66% p character. All right. That just comes from the fact that 3 orbitals, if you have one of them that's s, that makes up 33% of it, and other 66, right? All right, here we go. Let's draw out everything using the orbitals. So sp2, right? Remember there's 3 sp2 orbitals. So we're going to draw it like this. So remember the tiny lobe is always going to be pointing inside the carbon, sort of in the carbon, if you will. And the bigger lobe is going to be pointing towards the hydrogen. So there's going to be one lobe. This is one sp2 orbital. This is 2 sp2 orbital. And this is 3 sp2 orbitals, right? I've drawn all 3. And I'm going to do the same thing for the other carbon. One sp2 orbital. There's going to be 2 sp. It's going to be another sp2 orbital. And that's going to be my third sp2 orbital. Now remember that we still have one 2p orbital remaining. So I'm going to draw the 2p orbital now. The 2p orbital, remember, it looks like a dumbbell. And it's going to be symmetric, right? Unlike my sp2 orbitals. So it's going to look like this. And all right, I know that's not symmetric, but just pretend like it is. And also recall that the hydrogens, they also have their own 2s orbital. Like this, head to head here, head to head here, head to head here. All of these are sigma bonds. Sigma bonds. And there's also going to be an overlap of the sp2 orbitals, right? Because there, one sp2 orbital overlaps with the hydrogen, the other one overlaps with the other hydrogen, and then the last sp2 orbital overlaps with the sp2 orbital of this other carbon. So there's going to be another pi. Why did I say pi? There's going to be another sigma bond here, right? Notice there's overlapping here. However, then we have the p orbitals, right? There's a p orbital remaining here for this carbon, and there's also a p orbital remaining here for this carbon. And notice how they're not overlapping head to head, rather they're overlapping side to side, right? They're overlapping sort of sideways, parallel to each other. And this is something known as a pi bond. This is something known as a pi bond, okay? So the pi bonds, they come from leftover 2p orbitals that remain unhybridized, okay? So if we were to take a look at a molecule of ethene, right? Recall how it looks like this. So notice how all single bonds, in this case, represent our sigma bonds. However, this double bond right over here, you can think about it as one bond comes from the sigma bond, aka this overlapping head-to-head, and then this other bond comes from a pi bond. This leftover p orbital creates this pi bond, and notice how one bond plus two bond gives me this double bond right over here, right? So I'm going to make like a rules chart, but essentially single bonds, what we're going to learn later is that single bonds, they have only one sigma bond. Double bonds, they actually have one sigma bond and one pi bond. And it turns out that triple bonds, which we'll talk about later, but just as a little preview, they have one sigma bond and they're going to have two pi bonds. Okay? Now, some of you guys might be wondering, why didn't all the orbitals hybridize? Why did I have to leave this one 2p orbital unhybridized? Right? There's this one 2p orbital remaining. Why couldn't all these orbitals combine? And this orbital right over here, why does it have to be a p orbital? Why couldn't this orbital be an sp3 orbital, right? If all these combined, right, if we combine all the orbitals, why couldn't all these orbitals be sp3, right, aka all of them combined, and, you know, then they can overlap. And the reason why this happens, the reason why this undergoes only sp2 hybridization is because this is an important point, but like hybridized orbitals, they can't form pi bonds. This is because they're lopsided, so they can't really line up straight the way that 2p orbitals can. So this is why you have to have one p orbital remaining so that they can bond like this. Otherwise, you just have the last hybridized orbital really doing nothing, right? Because it can't form a pi bond. You can see here that this is a molecule of ethine, and it has 180-degree bond angles, right? So we are going to try to make sure that we get 180-degree bond angles from our hybridization. Now, what's going to happen is, once again, we're going to have the same steps as before. 2s orbital is going to promote one electron to the 2p orbital, right? Once again, so that all the orbitals are available to use. And then one s orbital and one of the 2p orbitals is going to combine. Both of these are going to have one electron, right? You use two orbitals right over here. You're going to get two orbitals, but you're also going to have these two 2p orbitals remaining, right? So you're still going to have these 2p orbitals remaining. Because I have no space, I'm just going to draw them here. And then you're still going to have the 1s orbital, but it doesn't really do anything in the bonding, so we're going to ignore that. I mean, more specifically, you could say this is a 2sp orbital, and this just highlights that this is an sp hybridization happening in the second shell. So yeah, that's a little bit more specific. Anyways, this is what's going to happen. So once again, the sp orbital is still going to look like this, where one side is bigger than the other. So let's see how that plays out when I draw out my model using orbitals. So this carbon right here is going to have two sp hybridized orbitals. So it's going to have one orbital, one hybridized orbital here, and another hybridized orbital here, I should say. And this is for this carbon right here. And let's draw for the other carbon. The other carbon is going to have one hybridized orbital here and another hybridized orbital, just say here. And then we can't forget that there's still two p orbitals remaining, right? There's still two p orbitals remaining. There's still two of these things remaining. Remember that p orbitals are going to be looking something like this, and then the other one. All right, and then there's another p orbital, and let's just say another p orbital is right over here. All right, so it's on the, just say there, and for the other atom, I'm going to draw p orbitals the same way. All right. Oh my god, these are horrible p orbitals. They look like hybridized orbitals. Sorry guys if it looks a little confusing. All right, so now I have drawn the two carbons, and now it's time to draw my hydrogen. So my hydrogen, remember that has this 1s orbital right over here, and it also has this hydrogen also has a 1s orbital that overlaps with the hybridized orbital. And there we go. This is sort of how ethine looks like. Now notice how there's one sigma bond here, one overlap here, there's one overlap here, and there's one overlap right over here, right, because you have one of the sp orbitals overlapping with the other sp orbital of this carbon, right? You see that? This is the region right over here. And finally, you're going to have two pi bonds, right? Because notice how these two p orbitals line up. So that's going to be a pi bond, right? Because they overlap parallelly, right? Is that even a word? And then you also have the other p orbitals. They also overlap. And it's also going to be parallelly, quote unquote, right? So notice how for my triple bond that I have, right? Because remember, this is a triple bond between the two carbons. Well, notice how I have one sigma bond and two pi bonds. So a triple bond is just one sigma bond and two pi bonds, which is what we predicted here. Or not predicted, but that's what I said here. When I looked at CH4, for example, how did I know that this was going to undergo sp3 hybridization? How do I know that ethine is going to undergo sp hybridization, right? How do I know this? Well, that's when you use steric number. So, for example, if I were to look at CH4, remember that CH4 underwent sp3 hybridization. How do I know this? Well, let's take a look at CH4. CH4 looks like this. I mean, it doesn't look like this. I said this before, but let's just simplify this. All right, how many atoms are bonded to the atom that I'm focusing on? So let's say if I'm trying to find out what type of hybridization this carbon will go through, how many atoms are bonded to that atom? 4 atoms, right? You have 1, 2, 3, 4. So there's 4 atoms. How many lone pairs does this carbon have? 0. 4 plus 0 is 4. And atoms with a steric number of 4, steric number of 4, contributes to a sp3 hybridization. Let's do another problem. Let's say if I have, let me just do the examples that I did before to show y'all this. Let's just say I have this right over here. Right, the ethene, we did this hybridization before. We saw that this was sp2 hybridization. Well, how do I do this using the steric number method? Well, if I'm trying to focus on this carbon right over here, well, how many atoms are bonded to this carbon? 1, 2, 3. How many lone pairs does it have? 0. 3 plus 0 is 3. And steric number 3 corresponds to an sp2 hybridization. And then, that's pretty much it. So look at CO2. Let's see what the hybridization is for this carbon and for this oxygen. If we take a look at carbon, notice how carbon is bonded to 2 things, right? So number of atoms bonded to the atom I'm focusing on is 2, and it has 0 lone pairs. So steric number is 2, sp hybridization. What about this oxygen? Oxygen is only bonded to 1 thing, right? So 1. Notice how it has 2 lone pairs. So 1 plus 2 is 3. 3 corresponds with an sp2 hybridization. So in fact, both of these oxygens, sp2 hybridization. Might be wondering, what the hell? How is the carbon and the oxygen has the hybridization? And let me show you a diagram of what's happening. So yeah, recall that carbon, when it's undergoing sp hybridization, right? There's going to be 2 sp orbitals and two 2p orbitals, each with 1 electron. So this is how it's going to look like, right? Each one of these has 1 electron. So that means it's ready to bond. If we take a look at the oxygen, notice how oxygen, right? This is actually oxygen unhybridized, right? Oxygen has an electron configuration of 1s2, I didn't draw it here, but 1s2, 2s2, and 2p4. So notice how there's 4 electrons combined into 2p orbitals. Now, because all of my 2p orbitals are filled, Oxygen actually does not promote its electron to the other orbital. It does not give away the electron to the next orbital. No, it does not do that because all the orbitals are filled. What's actually going to happen is that this 2s orbital is actually going to hybridize with the other orbitals. So this is going to undergo, remember, sp2 hybridization, is that you're going to get these 3 sp2 orbitals, right? Notice how this sp2 orbital has 2 electrons because this 2s orbital has 2 electrons. This sp2 orbital has 2 electrons because this 2p orbital has 2 electrons. And then this sp2 orbital has 1 electron because this 2p orbital has 1 electron. All right, so whatever the electrons, the amount of electrons in each of these orbitals, that's reflected in the hybridized orbital. All right. Now, these 2 orbitals that are completely filled with electrons, those become our lone pair orbitals, right? This is why oxygen has 2 lone pairs right over here. You can think about it as these 2 lone pairs right over here are the sort of sp2 orbitals that are filled with the 2 electrons, right? These are our lone pair orbitals, and then this is the orbital that actually does something. All right, as well as the pi bond from the 2p. So this is actually how the structure is going to look like. So sp2 orbitals right over here. Think about 2 sp2 orbitals. These are sp2, and they're already filled with 2 electrons. So these become our sort of lone pairs, right? These become our lone pairs. Now this sp2 right over here has 1 electron, meaning that it's able to share electrons. This sp2 orbital is able to share this 1 electron with this sp2 orbital that also has 1 electron, right? And finally, you have this p orbital. You have this p orbital remaining. Remember, you still have this 2p orbital, and it has 1 electron, and that is going to form a pi bond with the 2p orbital of this carbon atom. This is why when you're drawing an atom of CO2, this is a double bond because one of the bond comes from this head-on overlap of a sigma bond, but then this other comes from this p orbitals overlapping, right? So that is basically the structure for CO2. I'm too lazy to do the same thing for this other oxygen, but it's basically the same thing as this oxygen. It undergoes the same thing as this oxygen. All right. So if you just want a quick summary of everything that we learned, or if you're kind of studying for a test and you just want a quick study guide, well, just remember that hybridization, all of that is used to maintain the VSEPR rules. All right. I want to maintain this VSEPR rule, so that involves promoting electrons, that involves hybridization of orbitals. Remember that steric number is used to calculate what type of hybridization an atom will go through. And remember that single bonds have a sigma bond, double bonds have 1 sigma bond and 1 pi bond. And remember that triple bonds have 1 sigma bond and 2 pi bonds. And that's pretty much the summary of this video.